Hold your hand up to the light for a moment. It feels solid, warm, entirely your own. And in the time it takes to read this sentence, about 100 trillion tiny particles from the sun have passed straight through that hand without touching a single atom of it. They are called neutrinos, and they are the closest thing nature has to a ghost, a kind of matter that barely notices ordinary matter at all. Almost every one of them will cross the whole Earth and come out the far side unchanged. This is the story of that particle, how we found something we cannot feel, and why the largest machine ever built, at CERN, is still hunting particles that leave no trace at all. If slow, clear science is your kind of quiet, consider subscribing. Now, a simple puzzle to start with. How do you catch something that goes through everything? The story begins with a broken ledger. In the early years of the 20th century, physicists studied a kind of radioactivity called beta decay. In beta decay, the nucleus of an atom throws off a fast electron and changes into a slightly different element. It was one of the cleanest processes they knew, and it should have obeyed the oldest rule in physics: energy is never lost, only moved around. The nucleus starts with a fixed amount of energy. The pieces it turns into should carry exactly that same amount away, no more and no less. So when the electron flew out of the nucleus, it should always have carried a specific, predictable amount of energy. Every decay of the same type should have sent its electron out with the same speed, like identical stones thrown with identical force. That was the prediction. It was simple, and it followed straight from the conservation of energy that everything else in physics seemed to honour. The measurement said something else. When physicists like Lise Meitner and Otto Hahn, and later James Chadwick, measured the energy of those electrons, they did not find a single sharp value. They found a whole smear of energies. Some electrons came out fast, carrying nearly the full amount the physics allowed. Most came out slower, carrying less. A few crawled out with almost nothing. The energy that left the nucleus in each decay was different every time, spread across a continuous range from nearly zero up to a firm ceiling. Think of it like a vending machine that should hand you the same change every time you feed it the same coin. Instead, sometimes it gives you the full change, and sometimes it gives you half, and sometimes almost none, and the leftover simply never appears in the tray. Somewhere between the nucleus and the detector, energy was going missing. Not a fixed amount you could account for and set aside, but a different, unpredictable slice each time. This was not a small discrepancy at the edge of the instruments. It was large, it was repeatable, and it sat right on top of the most trusted principle in all of physics. If energy really was vanishing in beta decay, then the conservation of energy, the rule that let physicists trust every calculation they made, was not a law at all. It was only a suggestion that held most of the time and quietly failed inside the atom. By 1930, this had grown from a curiosity into a genuine crisis. The Danish physicist Niels Bohr, one of the founders of quantum theory, was troubled enough that he was willing to consider the unthinkable. Perhaps, he suggested, energy was not perfectly conserved after all. Perhaps inside the nucleus it was only conserved on average, over many decays, while any single decay could gain or lose a little. For a mind as careful as Bohr's to reach for that idea shows how deep the trouble ran. He was prepared to weaken one of the pillars the whole building stood on. That is the tension you need to hold as everything else unfolds. On one side sat a measurement no one could argue with, a spread of electron energies seen clearly in the laboratory. On the other side sat a law no one wanted to give up, the conservation of energy that made physics trustworthy. Both could not be fully right at the same time, or so it seemed. Something had to give, and the two obvious answers, a broken law or a broken measurement, both felt wrong. There was a third answer, quieter and stranger than either. What if the energy was not vanishing at all? What if it was leaving with something the detectors simply could not see? A piece of the decay carried off by a passenger no instrument had ever caught. Nobody had any evidence for such a thing, but one physicist was about to propose it anyway, half in apology, and set the whole hunt in motion. The physicist was Wolfgang Pauli, and he was not happy about what he was about to do. Pauli was Austrian, brilliant and famously merciless. He was the kind of scientist who could wither a colleague's work with a single sentence, and he held his own ideas to the same hard standard. He had already given physics one of its deepest rules, the exclusion principle, which explains why electrons in an atom stack into shells instead of piling into one place. So when Pauli reached for a desperate idea, it carried weight, and it also cost him something to say it out loud. His idea was simple and to him almost embarrassing. Suppose there was a second particle coming out of beta decay alongside the electron. Suppose it was neutral, carrying no electric charge, so no detector built to sense charge would ever notice it. Suppose it was very light and barely interacted with anything, so it could slip straight out of the experiment and off into the world unseen. If such a particle existed, it could carry away the missing energy. In each decay, the electron and this hidden partner would share the total between them in different proportions each time. That would explain the smear of electron energies perfectly, and it would save the conservation of energy whole. Pauli did not announce this in a grand lecture or a careful paper. In December of 1930, he wrote a letter. He addressed it to a group of physicists meeting in Tübingen in Germany, and he opened it with the words, "Dear radioactive ladies and gentlemen." He apologized that he could not attend the meeting in person, explaining that he needed to stay for a ball being held that same night. In the letter, he laid out his invisible particle, calling it a neutron, a neutral little thing, and admitted his discomfort plainly. He wrote that he had done a terrible thing by proposing a particle that could never be observed. A physicist, he felt, should not invent something that experiment could never test. That worry was the honest core of his hesitation. Science lives or dies by what can be measured. A particle that touches nothing, that leaves no track, no flash, no mark of any kind, sits dangerously close to a particle that is not there at all. Pauli knew this. He was proposing the least satisfying kind of solution, a hidden thing invoked precisely because it was hidden, and he called it a remedy he was not proud of. There was also a naming problem waiting to happen. Pauli's word neutron would soon be taken by James Chadwick, who in 1932 discovered a genuinely different particle, the heavy neutral partner of the proton that sits inside every nucleus. Chadwick's neutron was real, catchable, and thousands of times heavier than the ghost Pauli had in mind. The two ideas shared a name for only a short while before physics had to tell them apart. What matters is the shape of Pauli's move. Faced with missing energy, he refused to throw away the conservation law, and he refused to pretend the measurements were wrong. Instead, he added something new to the picture, an unseen passenger that balanced the books. It was a guess, offered with an apology, resting on no direct evidence at all. For years it would stay that way, a clever bookkeeping trick that might be true and might be nothing more than wishful arithmetic. Pauli himself once said gloomily that he had done something no theorist should do. He had predicted a particle he believed no one would ever detect. He was wrong about that last part, though it would take 26 years and a nuclear reactor to prove it. First, someone had to take his lonely idea and build it into a real theory of how the nucleus actually works. That someone was Enrico Fermi. Fermi was Italian, and he had a rare gift that most physicists only have half of. He was a superb theorist, able to build the mathematics of a new idea, and he was also a gifted experimenter, able to test it with his own hands in the laboratory. His colleagues in Rome gave him a nickname that captured how they felt about his reliability. They called him the Pope, because Fermi seemed never to be wrong. In 1933, Fermi took Pauli's shy little particle and gave it a proper home. He wrote down a full theory of beta decay, a real mathematical description of how the process works from the inside. In Fermi's picture, beta decay is not a particle sitting in the nucleus and being flung out. It is a transformation. A neutron inside the nucleus turns into a proton, and in the very act of that change, an electron and Pauli's hidden particle are created together, on the spot, and both fly out. They did not exist a moment before. The decay brings them into being. This was a genuinely new way to think about matter. Particles were not just moved around, they could be made. And Fermi gave the process a strength, a number that set how likely the decay was to happen and how fast. That number turned out to be very small. The interaction driving beta decay was feeble compared with the forces physicists already knew, weaker than the electric force by an enormous margin, and weaker still than the powerful force that binds the nucleus together. From this smallness would grow the name of a whole force of nature, but that comes a little later in the story. Fermi also settled the naming trouble, and he did it with a light touch. Pauli's word had been taken by Chadwick's heavy neutron, so Fermi, speaking Italian, gave the little particle a name that means the small neutral one. He called it the neutrino. The word carried exactly the right sense, a tiny thing, electrically neutral, easy to overlook. It stuck, and it is the name we still use today. There is a human detail here worth keeping. Fermi wrote up his theory of beta decay and sent it to the leading journal of the day, the British journal Nature. The editors rejected it. They said it contained speculations too remote from physical reality to interest the reader. One of the most important papers in the history of physics was turned away for being too far from the real world. Fermi published it elsewhere, and history sorted out who had judged it correctly. What Fermi had done was turn a bookkeeping trick into physics. Pauli had offered the neutrino as a way to save the energy ledger, almost an accountant's fix. Fermi took that same particle and wove it into a working machinery of decay, complete with a rate, a mechanism, and a name. The neutrino was no longer just the thing that carried off the missing energy. It was now a predicted product of a specific, calculable process, one that any nucleus undergoing beta decay would produce in vast numbers, and yet nothing had changed about the hardest fact. The neutrino, in Fermi's theory as in Pauli's letter, still interacted almost not at all. The theory that made it real also explained precisely why it was so nearly impossible to catch. To understand that, and to feel just how faint the neutrino's touch on the world truly is, we need to look closely at the force Fermi had stumbled onto, the weakest touch in all of nature. Nature, as far as we can tell, is run by 4 forces. 2 of them you meet every day. Gravity holds you to the floor and keeps the moon circling the Earth. The electromagnetic force lights your screen, binds atoms into molecules, and gives solid things their solidness. The other 2 hide inside the nucleus. One is the strong force, which glues the particles of the nucleus together against their own electric repulsion. The last is the weak force, and it is the one that makes the neutrino a ghost. The weak force is badly named, because weak undersells how strange it is. It is not simply a gentler version of the others. Its real oddness is its reach and its shyness. It acts only across distances far smaller than a single atomic nucleus, so short that 2 particles have to be almost on top of each other before it does anything at all. And even then, it acts rarely. A neutrino can pass close by a proton countless times and simply not feel it. The weak force is the only way an ordinary neutrino touches the rest of the world, and it barely reaches out at all. Here is the picture worth holding. Imagine trying to shake hands with someone, but your arm can only extend a hair's width, and even at that distance your hand usually passes right through theirs. Most of the time nothing happens. Once in a great while, contact. That is roughly the neutrino's relationship with matter. It is not that the neutrino is small and keeps missing things. It is that its one way of interacting is so short in reach and so faint in strength that solid matter is, to a neutrino, almost entirely empty space with a very rare snag. The numbers are hard to believe, so let us tie them to something you can picture. To have an even chance of stopping a typical neutrino from the sun, you would need a wall of solid lead. Not a thick wall, a wall about 1 light-year deep. Light itself, moving at its unmatched speed, would take a full year to cross that much lead. A neutrino would very likely sail straight through it and come out the other side untouched. That is not a flaw in the material. That is how weakly the neutrino grips the world. This is why the neutrino earns the word ghost so honestly. A ghost is supposed to drift through walls as if they were not there, and the neutrino does exactly that, not by magic but by the plain arithmetic of the weak force. Right now, as you read, neutrinos from the sun are streaming through your body, through the chair, through the ground, and out the far side of the planet into space. During the day they arrive from overhead. At night they come up through the whole Earth from below, having crossed the entire world as if it were open air, and yet the weak force is not nothing, and this is the crucial hinge of the whole story. If the neutrino interacted with nothing at all, ever, it would be a philosopher's ghost, forever beyond reach, and physics would have no business claiming it exists. But it does interact, just extraordinarily rarely. That rareness is the whole problem, and the whole opportunity at once. It means you cannot catch a neutrino with a small detector or a short experiment. It means you must gather an enormous number of neutrinos, or an enormous amount of matter for them to pass through, and then wait patiently for the vanishingly rare moment when one of them finally snags on a single atom and leaves a mark. For more than 2 decades after Fermi named it, no one managed that. The neutrino stayed a creature of theory, believed in because the energy ledger demanded it, never once seen. To turn belief into proof, 2 physicists would need a source pouring out neutrinos beyond counting, and the patience to watch for the 1 in a trillion that stopped. The 2 physicists were Clyde Cowan and Frederick Reines, and they were working at the Los Alamos laboratory in the United States in the early 1950s. Reines was the driving force, a man who wanted to catch the uncatchable simply because it seemed like the hardest and most beautiful thing a physicist could try to do. He later said he wanted to detect the neutrino precisely because everyone told him it was impossible. Cowan was his partner, steady and practical, the one who helped turn a wild ambition into a working machine. Their first idea for a neutrino source is startling, and it tells you how bold they were. They seriously considered using a nuclear bomb, a nuclear explosion, in the fraction of a second before everything is destroyed, releases a colossal burst of neutrinos, more in that instant than almost any other source on Earth. Cowan and Reines actually planned an experiment to place a detector near a bomb test, drop it down a shaft as the bomb went off, and catch the neutrino flash before the falling equipment was obliterated. The plan was real enough to have a name and a design. Then a wiser thought arrived. They realized they did not need the bomb. A nuclear reactor, running steadily, also pours out neutrinos in vast numbers, not in a single deadly instant but continuously, day after day. A reactor works by splitting heavy atoms, and the fragments left behind are rich in neutrons that undergo beta decay. Every one of those beta decays sends out a neutrino, or more precisely an antineutrino, the neutrino's mirror image partner. A large reactor floods the space around it with these particles, quietly and safely, for as long as it runs. That flood was their source. So in 1956, Cowan and Reines set up their experiment at the Savannah River nuclear plant in South Carolina. They placed their detector close to the reactor and deep enough to shield it from other stray particles. Then they watched. The idea was no longer to catch a single neutrino from a bomb in one violent moment. It was to sit beside the steady river of reactor neutrinos and wait for the rare few that would leave a clean, unmistakable signal in the tank they had built. The detector itself was a careful design, and its heart was ordinary water laced with a compound of the metal cadmium, arranged so that a passing neutrino, on the very rare occasion it interacted, would produce a specific 2-part flash of light. The whole apparatus was built to recognize that one particular fingerprint, and to reject nearly everything else, so that a real neutrino event could be told apart from the constant background noise of the world. When the signal came, it came exactly as predicted. The pattern they were looking for appeared in the tank, at the rate the theory said it should, and it went away when the reactor was shut down and came back when it was running again. That last check mattered enormously. It meant the signal was tied to the reactor, to the neutrinos and not to some quirk of the equipment. After more than 25 years as a creature of pure theory, the neutrino had finally left a mark that human beings could see. Cowan and Reines sent word of their success to the one person who most deserved to hear it. They sent a telegram to Wolfgang Pauli, the man who had proposed the particle in 1930 with an apology, convinced no one would ever detect it. Pauli received the news that his ghost was real. He's said to have celebrated with a bottle of champagne. The particle he had offered so reluctantly, half certain it could never be found, had been caught at last. The neutrino was now a fact of nature, not a hope, but knowing it existed only sharpened the next question. What exactly had happened inside that tank of water to betray a particle that touches almost nothing? To trust the discovery, physicists had to understand the trap itself. The trap worked by turning the neutrino's own rare interaction into a signal that could not be faked. The key reaction has a name, inverse beta decay, and it is worth walking through slowly, because it is the exact reverse of the process that started this whole story. In ordinary beta decay, a neutron becomes a proton and spits out an electron and an antineutrino. In inverse beta decay, an antineutrino arrives, strikes a proton, and runs the process backward. The proton absorbs the antineutrino and turns into a neutron, while flinging out a particle called a positron. A positron is the antimatter twin of the electron. It is just like an electron in every way except that it carries the opposite electric charge. An antimatter has a dramatic habit. When a positron meets an ordinary electron, and there are electrons everywhere in ordinary matter, the two annihilate each other. They vanish, and their mass turns entirely into light, into two flashes of a specific energy heading off in opposite directions. That annihilation is the first half of the fingerprint Cowan and Reines were watching for. The instant a neutrino interaction created a positron, that positron met an electron and produced a sharp, telltale burst of light. But one flash of light alone is not enough. All sorts of stray events can make a flash in a tank of water. So the experiment leaned on the second half of the reaction, and this is the clever part. The neutron created when the proton absorbed the antineutrino did not simply disappear. It drifted through the water for a tiny fraction of a second, slowing down, and then it was captured by an atom of cadmium. The metal dissolved into the water for exactly this purpose. Cadmium has a strong appetite for neutrons. When it swallows one, it settles into a calmer state and releases the extra energy as a second flash of light. So a genuine neutrino event wrote a two-part signature in time. First, the immediate flash from the positron annihilating. Then, a few millionths of a second later, the second flash from the neutron being caught by cadmium. Two flashes, in that order, separated by just the right tiny gap. No ordinary background event produced that exact double beat with that exact spacing. By demanding both flashes in sequence, the experiment could throw away almost all the noise and keep only the real thing. Picture it as a doorbell that rings twice with a precise pause between the rings and a lock set to open only for that exact rhythm. A single ring, however loud, does nothing. Two rings too close together or too far apart do nothing. Only the correct double beat, spaced just so, counts as a true visitor. That double beat was how Cowan and Reines knew a neutrino, and not some passing stray, had knocked. To see those faint flashes, the detector was watched by rings of light-sensitive tubes called photomultipliers, devices so sensitive they can register a mere handful of particles of light. The tank sat in darkness, shielded, so that the only flashes recorded were the ones born inside it. When the reactor ran, the correct double beats appeared at a steady, predictable rate. When the reactor was switched off, they nearly stopped. That contrast was the proof, clean and hard to argue with. There is a quiet beauty in how this trap used the neutrino's weakness against it. You cannot see the neutrino directly, and you never will. But you can watch for the small, specific wreckage it leaves behind on the rare occasion it interacts, and you can design that wreckage to be so distinctive that nothing else in nature mimics it. The neutrino stays invisible, its footprint does not. With the particle caught and the trap understood, one might think the story could rest. Instead, it opened up. Because the very success of this method soon revealed that the neutrino Cowan and Reines had caught was not the only kind. There was more than one neutrino, and finding the second changed the picture again. The clue that there might be more than one kind of neutrino came from a different particle entirely, the muon. The muon is one of nature's odd surprises. It behaves almost exactly like an electron, carrying the same negative charge, but it is about 200 times heavier and it is unstable, living for only a couple of millionths of a second before it decays. When it was discovered in the 1930s, no one had asked for it or expected it. The physicist Isidore Rabi is supposed to have greeted the muon with a famous complaint. He asked, "Who ordered that?" The muon mattered to the neutrino story because of how it decays. When a muon falls apart, it produces an electron, and alongside it, neutrinos. And when physicists looked closely at beta decay and at muon decay, they began to suspect that the neutrinos coming out of these processes were not quite the same. The neutrino tied to the electron and the neutrino tied to the muon seemed to behave differently, as if each heavy sibling came with its own dedicated ghost. Testing this required a new kind of experiment, and it was carried out in 1962 at the Brookhaven Laboratory in New York by a team including Leon Lederman, Melvin Schwartz, and Jack Steinberger. Their idea was to make a beam made only of the neutrinos that come from muon-related decays, and then see what those neutrinos did when they finally interacted. If there were just one kind of neutrino in all of nature, then when these beam neutrinos struck matter, they should sometimes produce electrons and sometimes produce muons, with no preference. If there were two distinct kinds, the neutrinos in this particular beam should produce only muons, never electrons, because they carried the muon's identity and not the electrons. Building that beam was a serious feat. They took a high-energy accelerator, smashed protons into a target to produce a spray of short-lived particles, and let those particles decay in flight, releasing neutrinos. Then they placed a wall of steel, thick steel salvaged in part from a decommissioned warship, to absorb every particle except the neutrinos, which of course sailed straight through the steel as though it were not there. On the far side, only the neutrinos remained, a clean beam of the muon type ready to be watched. The result was decisive. When those neutrinos interacted in the detector, they produced muons and did not produce electrons. The neutrino born alongside a muon made only muons when it struck matter. It knew its family and stayed loyal to it. This proved that the neutrino Cowan and Reines had caught, the one tied to the electron, was a genuinely different particle from the second one tied to the muon. Nature had at least two flavors of neutrino, and the word flavor is the term physicists actually use for these varieties. So the tidy picture of a single ghost particle was gone, and a pattern was emerging in its place. There was the electron, and its partner the electron neutrino. There was the heavier muon, and its partner the muon neutrino. Each charged particle came paired with a neutral, nearly invisible twin, matched to it and to no other. The building blocks of matter were arranging themselves into neat family groups, and the neutrinos were one member of each family. That pattern raised an obvious expectation. If the electron and the muon each had a neutrino partner, and if nature liked to repeat its patterns, then perhaps there was a third, heavier cousin still to be found, with a third neutrino of its own. The family seemed to want to come in a set. Whether that set stopped at 2, or continued to 3, or ran on forever, was the next thing the hunt had to settle. The third family arrived, and with it, the third neutrino. In 1975, at the Stanford Laboratory in California, a team led by Martin Pearl found a new particle heavier still than the muon. They called it the tau. The tau follows the same script as its lighter cousins. It carries the same negative charge as the electron and the muon, but it is far more massive, around 17 times heavier than the muon, and it decays almost the instant it is made. It was the third rung on a ladder no one had known would have 3 rungs. By the logic of the pattern, the tau had to come with its own neutrino, a tau neutrino, matched to it the way the electron neutrino is matched to the electron. Physicists were confident it existed long before anyone saw it, because the family structure demanded it. Still, confidence is not detection. The tau neutrino was the last of the three to be caught directly, and it was not pinned down until the year 2000 at the Fermilab laboratory near Chicago, in an experiment with the fitting name Donut. That completed the set of 3 neutrino flavors as observed particles, each tied to its own charged partner. So the neutrino comes in 3 flavors, matched to the electron, the muon, and the tau. But the deeper and stranger question is why the count stops at 3. Why not a 4th family or a 40th? Here nature gave an answer from an unexpected direction, and it came not from finding neutrinos but from watching a different particle decay. That particle is the Z boson, one of the heavy carriers of the weak force, discovered at CERN in 1983. The Z boson can decay into many things, including a neutrino paired with its antineutrino. Crucially, it can decay into every kind of light neutrino that exists, whether or not we can detect that neutrino directly. And each extra channel the Z boson has to decay into makes it fall apart a tiny bit faster. So the total lifetime of the Z boson secretly counts the number of light neutrino types, including any we have never seen, as long as they are light enough for the Z to produce. In the early 1990s, at CERN's Large Electron Positron Collider, physicists made Z bosons in enormous numbers and measured with great precision exactly how quickly they decayed. From that measurement, they read off the number of light neutrino flavors. The answer came out very close to 3. Not 2, not 4, but 3, matching the flavors already known. Nature seemed to have chosen a set of 3 complete families and stopped. This is one of the quietly profound results in particle physics, and it deserves a plain statement. By timing how fast a single kind of particle falls apart, physicists counted how many neutrino types the universe contains and found the answer is 3. The count did not come from hunting down each neutrino one by one. It came from the shadow that all of them together cast on the lifetime of the Z boson. There is a careful footnote to keep honest. This measurement counts only neutrinos that are light enough and ordinary enough to be produced when the Z boson decays and to feel the weak force in the usual way. If some stranger kind of neutrino existed that ignored the weak force, or was far too heavy, the Z boson's lifetime would not notice it, and this count would miss it. That loophole will matter much later, when the hunt turns to neutrinos even more elusive than the 3 we know. For now, the picture is settled and clean. 3 flavors of neutrino matched to 3 charged partners, 3 families of matter. It is a small and orderly set, and these 3 ghosts, so hard to catch here on Earth, turn out to be pouring through you at this very moment in unimaginable numbers from a source 93 million miles away. That source is the Sun, and to understand the flood of neutrinos it sends us, you have to go to its core. The Sun shines because in its center, under crushing pressure and at a temperature of about 15 million degrees, hydrogen is being fused into helium. 4 hydrogen nuclei, which are simply protons, are welded together in stages to make one nucleus of helium. That fusion is what powers the Sun and, through its light, nearly all life on Earth. And every time it happens, the process releases neutrinos. The reason neutrinos appear is buried in the arithmetic of the fusion itself. To turn protons into a helium nucleus, some of those protons must change into neutrons. That change is a form of beta decay, the same process that opened this whole story, and beta decay always releases a neutrino. So the Sun's core is not only a furnace of light, it is a factory of neutrinos, producing them in staggering numbers as a direct byproduct of making helium and shining. The scale is genuinely hard to hold in the mind, so anchor it to your own body. Every second, roughly 100 trillion neutrinos from the Sun pass through you. Hold up your thumbnail toward the Sun, and in every second, something like 60 billion solar neutrinos stream through that small patch of skin. They pour through your body whether you're indoors or outdoors, because ordinary matter barely slows them at all. This is not a rare event you might one day witness. It is happening constantly, everywhere on the sunlit side of the Earth, and on the dark side too through the whole thickness of the planet. Here is a detail that makes the sun's neutrinos even more remarkable than its light. The light you see from the sun is ancient by the time it leaves. A particle of light born in the core has to fight its way outward through the dense surrounding material, absorbed and re-emitted over and over, and it can take many thousands of years to finally reach the surface and escape. The neutrinos do no such thing. Because they barely interact, they leave the core almost instantly and fly straight out into space at nearly the speed of light. The neutrinos arriving at Earth now left the sun's centre about 8 minutes ago. The sunlight beside them began its journey in an age before recorded history. That makes the neutrinos something precious to a physicist. They are a direct message from the very heart of the sun, unaltered by the long journey through its outer layers. Sunlight tells you about the sun's surface. Solar neutrinos tell you about its core, the actual furnace, in something close to real time. If you could reliably catch and count them, you would be looking straight into the engine of the star, watching the fusion happen as it happens. And this is where a beautiful opportunity opened up. Physicists had a detailed theory of how the sun burns, worked out in careful detail by scientists like John Barkall, who spent much of his career calculating exactly how many neutrinos of each energy the sun's core should produce. The theory made a firm prediction. It said, in effect, this many neutrinos of this kind should be streaming out of the sun every second. That was a number you could test. If you could count the solar neutrinos arriving at Earth, you could check whether our understanding of how the sun shines was actually correct. The trouble, of course, was the counting. Neutrinos pass through everything, including any detector you might build. Catching even a handful of them out of that flood of trillions would take a device of extraordinary size and sensitivity, buried away from all the ordinary particles that might fool it. One man set out to do exactly that, deep underground, with a tank the size of a swimming pool. What he found would not confirm the theory. It would break it open. The man was Raymond Davis, and his laboratory was at the bottom of a gold mine. To catch solar neutrinos, Davis had to escape the constant rain of other particles that showers the Earth's surface from space, the cosmic rays that would swamp any neutrino signal. The only shield thick enough was the Earth itself. So in the late 1960s, Davis set up his experiment nearly a mile underground, in the home state gold mine in South Dakota, with all that rock overhead to block the noise and let only neutrinos, which sail through rock effortlessly, reach his detector. His detector was strange and elegant. It was a tank holding about 100,000 gallons of a common dry cleaning fluid, a chemical rich in chlorine. Davis was not trying to see flashes of light. He was fishing for individual atoms. Every so often, one of the countless solar neutrinos passing through the tank would strike a chlorine atom and through a weak interaction turn it into an atom of argon, a different element. Argon is a gas, and it is chemically inert, so those few new argon atoms would drift free in the fluid, waiting to be collected. The astonishing part is how few atoms Davis was counting. Out of the trillions upon trillions of neutrinos passing through his tank, he expected only a handful to convert a chlorine atom into argon in a given day. Over the course of a couple of months, the whole enormous tank might produce a few dozen argon atoms in total. Davis's task was to flush those few individual atoms out of 100,000 gallons of fluid, gather them up, and count them one by one. It has been compared to finding a specific few grains of sand across an entire beach and doing it reliably, run after run. That he managed this at all is a triumph of patience and care. Davis developed methods to sweep the argon out of the tank with helium gas, trap it, and count the atoms by watching them slowly decay. He repeated the process for years, refining it, guarding against every possible error, because the whole result rested on numbers so small that a few stray atoms could mislead him. Few experiments in physics have demanded such delicacy over such a long stretch of time. When the counting was done, Davis had a clear and troubling result. He was catching solar neutrinos, real ones, and that alone was a landmark. The first direct detection of neutrinos from the Sun. But he was catching far too few. The number of argon atoms his tank produced pointed to only about a third of the neutrinos that John Berkel's careful theory of the Sun said should be arriving. 2/3 of the expected solar neutrinos were simply not there. This was not a small mismatch that better measurements might smooth away. Davis and Berkel worked closely together, one counting and one calculating, and both were meticulous. Davis checked his atom counting again and again. Berkel checked his model of the Sun's core against everything else that was known. Year after year the gap held. The Sun appeared to be sending Earth only a third of its predicted neutrinos, and no one could say why. There were only a few ways out, and none was comfortable. Perhaps Davis was miscounting, missing most of the neutrinos through some flaw no one could find. Perhaps Berkel's model of the Sun was wrong, and the core was cooler or burned differently than believed. Or perhaps something happened to the neutrinos themselves on the way from the Sun to the tank, something that made 2 out of every 3 of them slip past undetected. For a long time, no one could tell which answer was right, and the shortfall settled into one of the most stubborn puzzles in physics. That puzzle earned a name, the solar neutrino problem, and it lasted for the better part of 30 years. For 3 decades, one of the best measured experiments in physics disagreed with one of the best calculated theories in physics, and no one could resolve it. This is worth sitting with, because it shows how science actually behaves when it meets something it does not understand. It does not rush to a fix. It holds the contradiction, tests every part of it, and waits until the evidence itself points the way. Through the 1970s and 80s, the pressure fell first on Raymond Davis. His result was so extreme, only a third of the expected neutrinos, that the natural suspicion was an error in the experiment. Catching a few dozen argon atoms in 100,000 gallons of fluid is so difficult that surely something was being missed. Davis felt this pressure keenly, and answered it the only honest way by checking his work relentlessly for years and finding no mistake. His count held firm. The neutrinos really were arriving in short supply. Then the pressure shifted to John Berkel and his model of the Sun. Perhaps the theory overestimated how many neutrinos the core should make. The number of neutrinos produced depends steeply on the core's temperature, so even a small error there could throw the prediction off badly. Berkel examined this with great care, but the same model of the Sun predicted many other things: the Sun's brightness, its size, the way sound waves ripple through it, and all of those matched observation beautifully. To lower the neutrino count enough to fix the problem, you would have to break the parts of the model that already worked. The theory of the Sun was too successful elsewhere to be simply wrong here. So the 2 obvious escapes both failed under scrutiny. The experiment was sound, the solar model was sound, and yet they disagreed by a factor of 3. New experiments only deepened the mystery. Other detectors, built later with different methods and sensitive to neutrinos of different energies, also found a shortfall. They did not all find the same fraction missing, which was itself a clue, but they agreed on the central fact. Fewer solar neutrinos were reaching Earth than the Sun should be sending. The problem was real, and it was not going away. That left the third possibility, the one that had always seemed the strangest. Maybe nothing was wrong with the counting or with the Sun. Maybe the neutrinos were leaving the Sun in exactly the numbers Berkel predicted, but something was happening to them during the 8-minute journey to Earth, something that changed them, so that by the time they reached Davis's tank, 2 out of every 3 were no longer the kind of neutrino his chlorine could catch. Recall that Davis's detector was sensitive only to electron neutrinos, the flavour tied to the electron. The Sun's fusion produces exactly that flavour and no other, so the calculation and the experiment were both counting electron neutrinos, and both should have matched. Unless somewhere between the core of the Sun and the bottom of the mine, some of those electron neutrinos had quietly turned into a different flavour, into muon neutrinos, or tau neutrinos that Davis's tank was blind to. This idea had actually been floated years earlier by the physicist Bruno Pontecorvo, a brilliant and restless thinker who had proposed that neutrinos might change from one flavour to another in flight. At the time it seemed exotic, almost too clever, but as every other explanation for the missing neutrinos fell away, this strange possibility began to look less like a wild guess, and more like the only door still open. The neutrinos might be changing on the way. The idea is called neutrino oscillation, and it is genuinely one of the stranger things in nature, so let us build it slowly. The claim is this: a neutrino born as one flavour, say an electron neutrino from the Sun, does not stay that flavour as it travels. As it flies through space, it changes, shifting into a muon neutrino or a tau neutrino, then possibly back again, cycling among the three flavours as it goes. It is not that the neutrino is disguised. It genuinely becomes a different flavour, and then another, as smoothly as a wave rising and falling. To feel why this can happen, you have to accept a quiet piece of quantum strangeness. The three neutrino flavours, electron, muon, and tau, are not the same as the three neutrinos of definite mass. Each flavour is actually a blend of the mass types, mixed together. When the Sun makes an electron neutrino, it is really launching a particular combination of these underlying mass states, all travelling together, and because the mass states have very slightly different masses, they travel in very slightly different ways, and the blend among them shifts as the neutrino moves. Here a comparison helps, drawn from sound. Strike two piano strings tuned to almost the same note, and at first their vibrations line up and reinforce each other. But because the two notes are slightly different, they slowly drift out of step, then back into step, producing that slow, throbbing swell you can hear as the combined sound waxes and wanes. That throb comes purely from the tiny difference between the two frequencies. Neutrino oscillation is the same kind of effect. The mass states are like those slightly mistuned strings, and as they drift in and out of step, the flavour of the neutrino swings from one kind to another and back. Notice what this comparison quietly demands, because it is the heart of everything that follows. Two piano strings can only drift out of step if their notes are actually different. If the strings were perfectly identical, they would stay locked together forever, and there would be no throb at all. In the same way, the neutrino's mass states can only drift out of step, and the flavour can only oscillate if those mass states have different masses. And two things can only have different masses if they have mass in the first place. So the very fact of oscillation, if it is real, forces a conclusion. Neutrinos must have mass. That was the deep stake hidden inside the solar neutrino problem. If neutrinos oscillate, then the electron neutrinos streaming out of the Sun would, over the 8-minute journey, partly convert into muon and tau neutrinos. By the time they reached Raymond Davis's tank, which could only catch the electron flavour, a large fraction would have changed into flavours his chlorine was blind to. He would count only the electron neutrinos that remained, and find a shortfall, not because neutrinos were missing, but because they were hiding in flavours he could not see. The missing 2/3 were not gone. They had simply changed clothes on the way. It was an elegant possible answer. It saved Berkol's model of the Sun, which had produced the right number of neutrinos all along. It saved Davis's experiment, which had counted correctly the electron neutrinos that survived. And it dissolved the contradiction between them, explaining the exact shortfall as the natural result of flavours shifting in flight. Everything fit, if only oscillation were real. But elegance is not proof, and physics rightly demands more. An idea that ties up every loose end can still be wrong. To settle it, someone had to catch the neutrinos in the act of changing, or better still, catch all three flavours together and show that the ones missing from the electron count reappeared in the others, so that the total came out whole. That decisive test was coming from two enormous detectors buried deep beneath the surface of the Earth. The first great confirmation came from Japan, from a detector called Super-Kamiokande, buried about 1 kilometre underground in a zinc mine. Super-Kamiokande is a magnificent instrument, a vast tank holding 50,000 tons of ultra-pure water, its walls lined with more than 11,000 of those sensitive light-detecting tubes. When a neutrino very occasionally interacts in the water, it produces a faint cone of blue light, and the ring of that light on the detector walls reveals what kind of interaction happened and which way the neutrino was going. In 1998, the Super-Kamiokande team announced a result that pointed straight at oscillation, though it came not from the sun but from the sky. High in the atmosphere, cosmic rays constantly strike air molecules and produce showers of particles, muon neutrinos, all around the globe. The detector could compare the muon neutrinos coming down from the sky overhead with those coming up through the whole Earth from the other side of the planet. The ones from below had travelled thousands of miles farther. If neutrinos oscillate, the ones that travelled farther should have had more time to change flavour, and so fewer of them should arrive as muon neutrinos. That is exactly what Super-Kamiokande found. The muon neutrinos coming up through the Earth were depleted compared with those coming down from directly overhead. The longer the journey, the more had vanished from the muon count. This dependence on distance was the signature of oscillation, hard to explain any other way. It was the first strong direct evidence that neutrinos really do change flavour as they travel, and it told the world that the neutrino carried mass. Still, one gap remained. Super-Kamiokande had shown muon neutrinos disappearing, but to close the solar neutrino problem completely, physicists wanted to catch the missing solar neutrinos in their new flavours to prove the electron neutrinos from the Sun were not lost but transformed. That final proof came from Canada, from the Sudbury Neutrino Observatory, set 2 kilometres down in a nickel mine, even deeper than its Japanese cousin. Sudbury had a special trick. Its central tank held 1,000 tons not of ordinary water, but of heavy water, water in which the hydrogen carries an extra neutron, on loan from Canada's nuclear program. Heavy water let the observatory do something no other detector could. It could catch electron neutrinos specifically, and separately it could catch all 3 flavours together, muon and tau included, through a different reaction. That meant Sudbury could measure both the electron neutrinos arriving from the Sun and the grand total of neutrinos of every flavour and compare the two. The result, announced in the early 2000s, was the clean and beautiful ending the puzzle deserved. The count of electron neutrinos from the Sun was low, only about 1/3, exactly the shortfall Davis had seen decades earlier. But when Sudbury added in the muon and tau neutrinos, the total came out to the full number that John Berkel's model of the Sun had predicted all along. The neutrinos were all there. 2/3 of them had simply changed flavour on the journey into kinds that Davis's chlorine could never catch. That closed the case. The Sun was making exactly as many neutrinos as the theory said. Davis had counted correctly, Berkel had calculated correctly, and the missing 2/3 had been quietly turning into other flavours the whole time, just as oscillation required. The 30-year solar neutrino problem was solved, not by finding an error, but by discovering something new and real about the neutrino itself. And that discovery carried a consequence the old physics had firmly ruled out. The consequence was mass. If neutrinos oscillate, then neutrinos have mass, and that single fact broke a rule that had stood at the centre of physics for decades. The reasoning is the one the piano strings gave us. Flavours can only cycle if the underlying mass states drift out of step, and they can only drift out of step if they have different masses, which means they must have mass at all. Oscillation is seen. Therefore neutrinos weigh something. However tiny that something is, it is not zero. To feel why this was such a shock, you have to know what the reigning theory said. The standard model of particle physics is the great achievement of 20th century physics, the framework that describes all the known particles and 3 of the 4 forces with breathtaking accuracy. It has passed test after test, predicting the results of experiments to many decimal places, and in its original form the standard model was built with neutrinos having exactly 0 mass, not small mass, 0. Masslessness was written into its foundations as a clean assumption. So the discovery of neutrino oscillation did something rare and important. It proved the standard model, for all its stunning success, was incomplete. Here was a plain, well-measured phenomenon, neutrinos changing flavour, that the theory in its standard form simply could not accommodate. The neutrinos were carrying a small mass the model had said they could not have. This is one of the very few places where experiment has clearly reached beyond the standard model and shown there is more physics out there, waiting to be understood. That is why the 2015 Nobel Prize in Physics went to Takaaki Kajita of Super-Kamiokande and Arthur MacDonald of the Sudbury Observatory for the discovery of neutrino oscillations and the proof that neutrinos have mass. Raymond Davis, whose lonely decades of counting argon atoms started it all, had already received his own Nobel in 2002, sharing it late in a long life for opening the door that the others walked through. The recognition marked how deep the result ran. It was not just the solution to one puzzle, it was the first solid crack in the most successful theory physics had. The crack raises a question that is still open today, and it is a good honest place to admit what we do not know. The standard model gives every other particle its mass through a specific mechanism involving the Higgs field, the field tied to the Higgs boson found at CERN in 2012, but it is not yet clear that neutrinos get their mass the same way. Their mass is so strange, so vastly smaller than any other particles, that many physicists suspect it comes from some different and deeper source, perhaps tied to physics we have not yet discovered. The neutrino's weight may be a clue to something larger. There is an even stranger possibility hidden here, one physicists take seriously. The neutrino might be its own antiparticle. For every other matter particle, the electron and its antimatter twin the positron, matter and antimatter are clearly distinct. But the neutrino is neutral and elusive enough that it might be the one particle that is identical to its own mirror image. If that were true, it would open a path to explaining the neutrino's tiny mass, and it might even help explain why the universe is made of matter at all. Experiments around the world are hunting for the rare signal that would settle it. So oscillation did not just solve an old problem, it handed physics a new frontier, a particle with a mass that should not exist by the old rules, born perhaps from mechanisms we have yet to find. And that only made the next question more pressing. If the neutrino has mass, then exactly how much? Just how heavy, or rather how impossibly light is this ghost? The honest answer is that the neutrino is almost unimaginably light, so light that we still have not managed to weigh it directly, only to close in on it from above. To hold the scale, start with the electron, itself one of the lightest particles known. The neutrino is at least hundreds of thousands of times lighter than the electron, and possibly far lighter still. It is by a wide margin the lightest particle that has any mass at all, sitting just barely above nothing. Oscillation experiments, for all they revealed, cannot give us the actual weight. They are sensitive only to the differences between the neutrino masses, the gaps between the three mass states, not the masses themselves. It is like knowing that three people differ in height by a couple of inches without knowing whether they are children or giants. The oscillation data pin down the small differences with real precision, but leave the overall scale floating. To fix the scale, you need a different kind of measurement entirely. One approach goes back to where the whole story began, to beta decay. When a nucleus undergoes beta decay, the electron and the neutrino share the released energy. If the neutrino has mass, then making that neutrino costs a little energy, and that cost slightly lowers the maximum energy the electron can carry. By measuring the energy of the fastest electrons from beta decay with extreme precision, and looking at the exact shape of the cutoff at the top, physicists can read off the neutrino's mass, or at least set a ceiling on it. The effect is minuscule, a tiny distortion right at the very edge of the spectrum. An experiment in Germany called Katrin is doing exactly this, with staggering care. It uses the beta decay of tritium, a heavy form of hydrogen, and a spectrometer the size of a building to measure those electron energies as finely as anyone ever has. Katrin has not found the neutrino's mass, because it is too small even for this instrument to see directly. but it has pushed the ceiling steadily downward, showing that the neutrino weighs less than a tiny fraction of the electron's mass, tighter than any beta decay limit before it. Each result narrows the box the true value must lie in. There is a second, completely different way to weigh neutrinos, and it comes from the largest thing there is, the whole universe. Because neutrinos are so numerous, left over in vast quantities from the hot early cosmos, their combined mass affects how the universe grew. Even a tiny mass per neutrino, multiplied across the countless neutrinos filling all of space, adds up to a gravitational influence that shaped how galaxies and clusters formed. By studying the large-scale structure of the universe and the faint afterglow of the Big Bang, cosmologists can estimate the total mass of all neutrino types added together, and their limit is even tighter than the laboratories. So we approach the neutrino's mass from two directions at once, from the smallest scale of a single decaying nucleus, and from the grandest scale of the entire cosmos, and both agree it is extraordinarily small. Why pin down a number so tiny it barely seems to matter? Because that number is a signpost. The precise mass of the neutrino, and the pattern of the three masses, points toward whatever deeper theory lies beyond the standard model. A particle this strangely light is telling us something, and the exact value is part of the message. We have now followed the neutrino from a broken energy ledger to a particle with mass, caught in reactors, counted from the sun, and seen changing flavour deep underground. Everything so far has come from neutrinos nature hands us for free, from stars and reactors and the sky. But there is another way to study the ghost, harder and more controlled, and it takes place inside the most powerful machine humanity has ever built. It is time to turn to CERN and to the problem of catching the uncatchable inside a collision. CERN sits on the border between Switzerland and France, near the city of Geneva, and its great instrument is the Large Hadron Collider, a ring of tunnel about 17 miles round, buried roughly 100 meters underground. Inside that ring, protons are accelerated to very nearly the speed of light and steered into head-on collisions tens of millions of times each second. Each collision concentrates a huge amount of energy into a tiny point, and out of that energy new particles are born, flying outward into detectors built to record them. It is the closest thing we have to recreating the conditions of the early universe, moment by moment. Studying neutrinos here is a very different challenge from studying them from the sun or a reactor. At a reactor, you have a steady, gentle flood of neutrinos and all the time in the world to wait. At the collider, neutrinos are made in the violence of a collision, mixed in with a spray of dozens of other particles, in an event that is over in an instant. You cannot sit and wait for a rare interaction the way Cowan and Reines did. You have to catch, in real time, the fleeting evidence that a neutrino was created and escaped in the middle of a chaotic burst of everything else. And escape it does, completely. A neutrino born in a collision at the heart of the Large Hadron Collider will pass straight out through the entire detector, through all those layers of dense metal and sensitive electronics, without leaving the faintest direct mark. The great detectors at CERN, machines the size of buildings and weighing thousands of tons, are essentially transparent to the neutrino. It is created in the collision, and it is simply gone, off into the rock and away before any instrument can touch it. This seems, at first, like an impossible situation. If the neutrino leaves no direct trace in the detector, how can you ever know it was there? You cannot see it come in, as at a reactor, because it is made inside the machine. You cannot wait for it to interact because it flies out too fast and too surely. The one particle you most want to study is precisely the one particle your enormous, exquisite detector cannot detect at all. It is the old problem of the ghost, returned in a harder form. Yet physicists at CERN do detect neutrinos from collisions, not by seeing them, but by noticing their absence with great precision. The trick is not to look at the neutrino. It is to look at everything else, add it all up with extraordinary care, and notice that some energy and motion have gone missing, carried off by something unseen. The neutrino betrays itself as a gap in an otherwise complete accounting, a hole in the ledger exactly the shape of what escaped. This is a beautiful inversion of the usual way of finding things. Everywhere else in physics, you detect a particle by catching something it does, a flash, a track, a click. Here, you detect the neutrino by catching what fails to happen, by the energy that should be present and is not. The collider hunt for neutrinos, and as we will see for even stranger things, is a hunt conducted almost entirely by absence, by the careful measurement of nothing where something ought to be. To make that possible, physicists rely on one deep and unbreakable principle, a conservation law even more powerful in this setting than the conservation of energy that started our story. It is the conservation of momentum, and it is the single tool that lets a collision reveal what quietly slipped away. Understanding that accounting trick is the key to everything CERN does with the invisible, and it is where we turn next. The tool is the conservation of momentum, and it is even more reliable than the conservation of energy that opened this story. Momentum is the measure of motion, how much a thing is moving and in which direction, combining its mass and its velocity. The rule about it is absolute. In any collision, the total momentum afterward must exactly equal the total momentum before. Nothing can change that sum. It is one of the deepest and most trustworthy statements in all of physics, tested countless times, and never once seen to fail. Now think about how protons collide inside the Large Hadron Collider. Two beams run in opposite directions around the ring and meet head-on. Along the direction of the beams, the two protons carry equal and opposite momentum, so their motions cancel, and the total along the beamline is complicated to track. But look at the collision from a different angle. Consider only the motion sideways, out from the beam, in the flat plane that cuts across the ring. Before the collision, neither proton is moving sideways at all. Their entire motion is along the beam, so the total sideways momentum before anything happens is exactly zero. That single fact is the whole accounting trick. Because the sideways momentum starts at zero, it must stay zero. When the collision throws dozens of new particles outward, all their sideways motions added together as arrows pointing out from the beam must cancel perfectly and sum back to nothing. If one particle flies to the left, something must balance it on the right. The books must close. The sideways ledger, empty before the collision, must be empty again after, no matter how violent the burst in between. So the detector measures every particle it can catch, and records how much sideways momentum each one carries, and in which direction. Then it adds all those arrows together. If the neutrino, or anything else invisible, never existed, that sum would come out to zero as the law demands. But when a neutrino is made and escapes, it carries real sideways momentum out of the detector with it, unrecorded. The visible particles left behind no longer balance. Their arrows add up not to zero but to some leftover amount pointing in one direction. That leftover is the fingerprint of what escaped. Picture a game of billiards where the balls scatter across the table, but one ball is perfectly clear and invisible. You never see it move, yet you can watch all the visible balls, measure exactly where each one went, and notice that their motions do not balance the way the laws of collision say they should. From that imbalance alone, you can work out that an unseen ball rolled off in a particular direction with a particular speed. You detect the invisible ball not by seeing it, but by the hole it leaves in the motion of everything else. This is precisely how CERN finds the neutrino in a collision. The neutrino leaves no track and touches no sensor, but it carries away sideways momentum, and that missing momentum shows up as an imbalance in the careful sum of everything the detector did catch. The size and direction of the imbalance tell physicists how much invisible momentum left and which way it went. The ghost becomes visible as a precisely shaped absence. Everything depends, though, on catching nearly all the visible particles. If the detector misses some ordinary particle that simply slipped out an unmonitored gap, that too would look like missing momentum and could be mistaken for a neutrino. The accounting only works if the ledger is almost complete, if there are very few places for ordinary matter to hide. That demand, that a detector see very nearly everything shaped the design of the great machines at CERN, and it gave the missing momentum a proper name and a precise meaning. That name is where we turn next. The name is missing transverse momentum, and every word of it carries meaning worth unpacking. Transverse simply means sideways, across the beam, in the flat plane where the motion started at zero. Momentum is that measure of motion we just met, and missing means the amount by which the visible momentum in that plane fails to balance. Put together, missing transverse momentum is the leftover sideways motion, the arrow that remains after every detected particle has been added up, pointing straight at whatever invisible thing carried it away. Physicists lean on the transverse plane, the sideways directions, for a specific and clever reason. Along the beam, the collision is messy. The protons are not simple points but bundles of smaller particles, and when they crash, much of their debris shoots forward down the beam pipe and slips away unmeasured, because you cannot put detectors directly in the path of the beams, so the accounting along the beam direction is hopelessly incomplete from the start. But sideways, across the beam, nothing should escape down the pipe, and the total began at exactly zero. That makes the transverse plane the one place where the books can truly be balanced, and where a genuine gap really means something escaped. So when a detector reports a large missing transverse momentum, it is making a strong claim. It is saying that, after measuring every particle it could, the sideways motions do not add up, and the imbalance is too large to be an accident. Something real and invisible flew out of the collision carrying that motion. Most often, that something is a neutrino. This is the everyday tool by which neutrinos are identified at the Large Hadron Collider, not seen but inferred every day from the shape of the gap they leave. The measurement has to be done with great care, because the imbalance is only as trustworthy as the accounting behind it. Every detected particle's motion must be measured accurately and added in correctly. A single mismeasured particle, its energy read too high or too low, can create a fake imbalance that mimics a neutrino, or hide a real one. So physicists spend enormous effort calibrating their detectors, understanding exactly how each part responds, so that when they claim momentum is missing, they can be confident it truly left with something unseen and was not merely lost to an error in the sum. There is a real subtlety worth naming honestly. Missing transverse momentum tells you that something invisible escaped and how much sideways motion it took, but by itself it does not tell you what that something was. A single neutrino and some other unseen particle could leave the very same gap. The imbalance is a footprint without a name attached. To learn what made it, physicists study everything around it, the visible particles produced alongside, their energies and patterns, and from that context they judge what kind of invisible thing most likely slipped away. The footprint alone says only that a ghost passed by. This is the quiet power and the quiet limitation of the method, held together. It can reveal the presence of the invisible with real confidence, turning a hole in the ledger into a measured quantity. But it speaks in the language of absence, and absence is ambiguous. That very ambiguity, it turns out, is not only a difficulty, it is also an opportunity, because if some entirely new invisible particle were being made in these collisions, it too would announce itself as missing transverse momentum, hiding in the same gap the neutrino uses. Before we chase that possibility, it helps to see the method's first great triumph, a discovery built on a neutrino no detector ever saw. The triumph came in 1983 at CERN, and it was the discovery of the W boson, one of the two heavy carriers of the weak force. Remember that the weak force is what lets the neutrino interact at all, the faint touch behind beta decay. That force is carried by particles, the way the electromagnetic force is carried by particles of light. There are two such weak carriers, the W boson and the Z boson, and they are heavy, far heavier than the proton, which is why the weak force reaches only across tiny distances and feels so feeble. Finding them was one of the great goals of physics in the early 1980s. The W boson has a telling habit when it decays. Often it falls apart into two particles, a charged one that a detector can catch, an electron for instance, and a neutrino that escapes completely. So the signature of a W boson is not a clean, fully visible event. It is a single energetic electron flying out one way, and a large missing transverse momentum pointing the opposite way, the invisible neutrino balancing the visible electron. The discovery of the W boson depended on reading that pattern, on trusting that the missing momentum was a real neutrino and not a flaw in the measurement. The experiment was led by Carlo Rubbia, a forceful and relentless Italian physicist, together with the engineer Simon van der Meer, whose ingenious technique for concentrating the particle beams made the collisions bright enough to work. Rubbia drove the project hard, converting an existing CERN accelerator into a machine that collided protons with their antimatter twins, antiprotons, at energies high enough to produce these heavy bosons. It was an audacious plan, and it demanded detectors that could measure the visible particles well enough to trust the invisible gap. When the results came, they were convincing. The teams found events with exactly the expected signature, a solitary high-energy electron and a matching amount of missing transverse momentum on the far side, just what a W boson decaying to an electron and a neutrino should produce. The mass they reconstructed for the parent particle matched the theory's prediction closely. The W boson was real, and so, once again, and in a new setting, was the neutrino that balanced its books. The prize followed swiftly. Rubbia and van der Meer received the Nobel Prize in Physics in 1984, remarkably fast recognition, a mark of how important the discovery was. Sit for a moment with what this means. One of the landmark discoveries in the history of particle physics, the detection of a carrier of a fundamental force, rested squarely on a particle that no detector in the experiment ever saw. The neutrino from the W boson's decay left the apparatus untouched, exactly as neutrinos always do. Its entire contribution to the discovery was the hole it left, the missing momentum that pointed back to it. Physicists staked a Nobel-winning result on the honesty of that absence. That is a striking measure of how far the method had come and how much trust it earned. From Pauli's apologetic guess to Cowan and Reines catching a faint double flash, the neutrino had become something physicists could count on so completely that they used its guaranteed invisibility as a tool. They knew it would escape, they knew how much momentum it would take, and they read the discovery of a new force carrier from the gap. To make that trust possible, though, the detectors had to be built so that almost nothing ordinary could slip away unseen. Only then could a gap be believed. That demand produced the great hermetic detectors of the modern collider. The word for what these detectors need is hermetic, which means sealed, closed all the way around, with as few gaps as possible. The reasoning follows straight from the accounting trick. Missing momentum only means something escaped if you're sure you caught everything that did not. Every ordinary particle that slips away unmeasured, out some unmonitored crack, looks exactly like an invisible particle and fakes a signal. So to trust the gaps, you must leave almost no cracks. The detector has to wrap around the collision point as completely as a solid shell, catching nearly every particle that flies out in nearly every direction. The two great detectors that do this at the Large Hadron Collider are called ATLAS and CMS. Each is enormous, a cathedral of instrumentation built around a single point where the proton beams cross. ATLAS is about the length of half a football field and stands several stories tall. CMS is more compact but even heavier, weighing more than the Eiffel Tower, much of that weight in iron. Both are built in layers, like the rings of an onion, wrapped around the collision points so that a particle flying outward in almost any direction must pass through them and leave its mark. Each layer has a job, and together they read out nearly everything. Closest to the collision sit fine tracking detectors that record the paths of charged particles as they curve through a magnetic field, revealing their momentum. Around those sit calorimeters, dense blocks that stop most particles entirely and measure the energy they deposit. Farther out sit chambers tuned to catch muons, the heavy cousins of the electron, which punch through everything else and would otherwise escape. Layer by layer, the detector tallies the energy and motion of the whole spray of debris, building the nearly complete ledger the accounting trick requires. Nearly complete, but never perfectly so. 2 narrow openings must remain, where the beam pipes enter and leave, carrying the protons in and the forward debris out. Nothing can block those, so some particles always escape straight down the beamline. This is exactly why physicists rely on the transverse plane, the sideways directions, where nothing should escape. The hermetic design seals the sides and the ends as fully as engineering allows, closing every direction except the unavoidable forward gaps, so that a sideways imbalance can be trusted as real. When it all works, the result is a machine that catches almost everything, and therefore notices almost anything missing. A collision happens, dozens of particles fly out, and Atlas or CMS measures nearly all of them, their energies and directions, in the billionths of a second before the next collision arrives. Then the sum is taken. If the sideways momentum balances, no invisible particle of note escaped. If it does not balance, something unseen carried the difference away, and its signature is recorded for study. The hermetic shell turns the whole detector into a trap for the invisible, a device whose completeness is precisely what lets absence speak. This is the environment in which the modern hunt for ghosts takes place, and its logic reaches beyond the neutrino. Any new particle that interacts as weakly as the neutrino, or more weakly still, would escape these detectors just as surely and announce itself the same way as missing transverse momentum in a hermetic machine. The design built to trap the known neutrino becomes, without changing a bolt, a trap for whatever unknown invisible things the collisions might make. But the neutrino itself had one more surprise at CERN, a place where, against all the logic of escape, one was finally caught in the act. For decades, a strange gap sat inside the world's greatest particle physics laboratory. The Large Hadron Collider produced neutrinos in staggering numbers in nearly every collision, yet not one had ever been directly detected there. The great hermetic detectors, Atlas and CMS, were built to notice neutrinos only by their absence, by the missing momentum they carried off. No experiment at a particle collider had ever caught a collider neutrino by its actual interaction, seen it strike matter and leave a mark. The most productive neutrino source ever built had never had its neutrinos directly observed. The reason was a matter of direction. Neutrinos from the collisions stream out most intensely straight along the beamline, in the narrow forward direction where the beam pipe runs. The big detectors wrap around the collision from the sides, precisely the region the accounting trick needs, but they leave that forward line open for the beams. To catch the collision neutrinos directly, you would have to place a detector far downstream, right in that forward stream, hundreds of meters from the collision point, after the rock and equipment had absorbed nearly everything except the neutrinos, which of course pass through it all. That is exactly what a small experiment called FASER was built to do. FASER sits in a side tunnel about 500 meters from one of the collision points at the Large Hadron Collider, directly in line with the beam. Between it and the collision lies a great deal of rock and magnet and machinery, which stops essentially every ordinary particle. Only neutrinos, and possibly some undiscovered weakly interacting things, can travel that whole distance untouched and reach the detector. FASER is small and inexpensive compared with the giants, but it sits in the one place where collider neutrinos arrive in a clean, intense stream. In the year 2023, FASER announced success. It had directly detected neutrinos produced in collisions at the Large Hadron Collider, the first time neutrinos from any particle collider had ever been caught by their interactions, rather than merely inferred from missing momentum. In its detector, neutrinos from the collision struck matter and left the tracks of the charged particles born in those interactions, real marks from real neutrino events at the high energies that only a collider can produce. The ghost that CERN had always known only as an absence had finally been seen there as a presence. This mattered for more than pride. The neutrinos from these collisions are the most energetic ever produced in a laboratory, far beyond those from reactors or the sun, and studying them opens a new window on how neutrinos behave at such extreme energies. It lets physicists test whether the neutrino keeps following the known rules when pushed to conditions never before reached in a controlled experiment. It also builds a bridge to the neutrinos that arrive from deep space at even greater energies, made by violent events across the universe, by letting us study collider neutrinos of comparable strength up close. So the neutrino story at CERN came full circle. First, it was the invisible passenger, known only by the gap it left, used as a tool to discover the W boson and to watch for anything else that escapes. Then, at last, in a modest tunnel far down the beamline, it was caught in the act, striking matter and leaving a track, the same kind of direct detection Cowan and Reines had first achieved almost 70 years earlier, now at energies they could never have reached. The ghost had been both inferred and seen in the same laboratory by different means, and that dual method, catching the invisible by its absence and where possible by its rare presence, is exactly the approach physicists now turn on something even more elusive than the neutrino. There is a ghost that outdoes the neutrino at hiding, one that may not feel the weak force at all, and it makes up most of the matter in the universe. That greater ghost is dark matter, and it is more thoroughly hidden than the neutrino ever was. The neutrino, faint as its touch is, does feel the weak force, and through it we can catch the rare neutrino and even make beams of them. Dark matter appears to feel no force we can use to see it. It gives off no light, absorbs no light, and reflects no light, which is why it is called dark, though transparent would be closer to the truth. It seems to ignore the electromagnetic force entirely, the force behind everything we ordinarily see, and it may ignore the weak force too. As far as we can tell, it makes itself known through gravity, and so far through gravity alone, and there is a great deal of it. When astronomers add up all the matter in the universe, the ordinary matter, everything made of atoms, every star, planet, cloud of gas and living thing, comes to only about a sixth of the total. The other 5/6 is dark matter, some substance that outweighs all the ordinary matter in the cosmos roughly 5-1. The stuff we are made of, the stuff of every object we have ever touched or seen, is the minority. Most of the matter in the universe is something else, something we have never held, never seen directly, and cannot yet identify. This is a humbling situation to state plainly. We do not know what most of the matter in the universe is. We know it is there, we can map roughly where it sits, we can measure how much of it there is, and yet its actual identity, what particle or substance it is made of, remains unknown. It is one of the largest open questions in all of science, and it sits right alongside the neutrino in this story, because the tools built to catch the one invisible particle are among our best hopes for catching the other. The connection runs deeper than method. For a time, many physicists suspected that dark matter and the neutrino might be cousins of a sort, both invisible, both revealed by gravity or by absence. The neutrino was even considered early on as a candidate for dark matter itself. It is invisible, it is abundant, it fills the universe. But the neutrino turned out to be far too light and too fast to be the answer. Moving at nearly the speed of light, neutrinos could not clump together the way dark matter must to build the structures we see. They stream too freely, so the neutrino was ruled out as the main dark matter, but the family resemblance, the shared invisibility, kept the two hunts close together. What makes dark matter believable, rather than a mere fudge for things we cannot explain, is that the evidence for it comes from several completely independent directions, all pointing the same way. It is not one odd measurement. It is many separate observations, made with different instruments, at different scales, by people asking different questions, that each independently demand some large amount of unseen mass. When independent lines of evidence converge on the same strange conclusion, physicists take it seriously, however uncomfortable it is. So before we follow the hunt for dark matter into the collider and deep underground, it is worth seeing clearly why we believe in it at all. What forces us to accept that most of the universe's matter is a substance we have never seen? The answer lies in the motion of galaxies and in the bending of light across the sky, in observations that leave, as far as anyone has found, no comfortable way out except a great deal of invisible mass. The first clue came from the way galaxies spin. A galaxy is a vast rotating disk of stars, and the stars orbit its centre much as the planets orbit the Sun. For the planets, there is a clear rule, worked out long ago. The farther a planet lies from the Sun, the slower it moves in its orbit, because the Sun's gravity weakens with distance and holds the distant planets more gently. Mercury races around quickly, close in where gravity is strong. The outer planets drift slowly, far from the Sun's grip. The pattern is precise, and it follows directly from how much mass sits at the centre and how gravity falls off with distance. Galaxies should follow the same logic. Most of a galaxy's visible mass, its glowing stars and gas, is concentrated toward the centre, so stars far out in the sparse edges should orbit slowly, feeling only weak gravity from the mass piled up in the middle. That was the firm expectation. Measure how fast stars move at different distances from a galaxy's centre, and you should see the speed fall off as you move outward, just as it does for the planets around the Sun. In the 1970s, the astronomer Vera Rubin measured exactly this, studying how stars and gas move in spiral galaxies, and she found something that did not fit. The stars far out at the edges were not slowing down. They were orbiting just as fast as the stars much closer in. Out where the visible galaxy thins to almost nothing, where there was little glowing matter left to hold them, the outer stars still raced around at high speed, as though gripped by far more gravity than the visible mass could supply. The rotation did not fall off. It stayed stubbornly flat all the way out. There was only one way to make sense of it within the known laws of gravity. There had to be much more mass in those galaxies than anyone could see, and it had to extend far beyond the visible edge, out into a great invisible halo surrounding each galaxy. That unseen mass, reaching well past the glowing stars, would supply the extra gravity needed to keep the outer stars moving so fast. The visible galaxy, it seemed, was only the bright centre of something far larger and entirely dark. Vera Rubin's careful measurements, galaxy after galaxy showing the same flat pattern, made the case hard to dismiss. A second, independent clue came from the bending of light. According to Einstein's theory of gravity, mass bends the path of light passing near it, so a heavy object acts like a lens, distorting the image of anything behind it. Astronomers can measure how much the light from distant galaxies is bent as it passes by closer clusters of galaxies, and from that bending they can weigh the clusters. Again and again, the mass required to bend the light as strongly as observed is far more than the visible matter in the clusters can account for. The light is bent as though the clusters were many times heavier than they look. These two lines of evidence, the flat rotation of galaxies and the excess bending of light, come from entirely different physics and entirely different measurements, yet they agree. Both say the same thing. There is far more mass in the universe than we can see, spread through galaxies and clusters in vast invisible quantities. Add in the way galaxies clump across the cosmos and the pattern of the Big Bang's afterglow, and the evidence stacks higher still. Something unseen dominates the matter of the universe. The question then becomes sharp and practical. If it is a particle, what kind of particle is it, and can we catch it? For a long time, one answer stood out as the favourite, and it has a memorable name. The leading candidate was a weakly interacting massive particle, which physicists abbreviate to WIMP. The name states the idea plainly. A WIMP would be massive, carrying real heft, likely tens or hundreds of times the mass of a proton, and it would interact only weakly, through something like the weak force, ignoring the electromagnetic force entirely so that it gives off no light. massive enough to supply the universe's missing mass, weakly interacting enough to stay invisible. It fit the job description almost perfectly. What made the WIMP especially appealing was a striking coincidence that came to be called the WIMP miracle. If you suppose that in the hot early universe these particles were produced and then gradually thinned out as the cosmos expanded and cooled, you can calculate how many would be left over today. The leftover amount depends on how strongly they interact, and when you plug in an interaction strength close to that of the known weak force, the amount of dark matter you get is just about exactly the amount astronomers actually measure. A particle interacting at the weak scale naturally leaves behind the right quantity of dark matter without any fine-tuning. That coincidence was too suggestive to ignore. It hinted that dark matter and the weak force might be tied together at a deep level, that the same feeble interaction which governs the neutrino might also govern the missing mass of the universe. And it carried a thrilling practical consequence. If dark matter interacts through something like the weak force, then the Large Hadron Collider, which routinely produces particles through the weak force, might be able to make dark matter directly in its collisions. The missing mass of the cosmos might be manufactured, a few particles at a time, inside a machine on Earth. This is why the hunt for dark matter came to the collider, and why it uses the very same accounting trick built for the neutrino. If a pair of dark matter particles were created in a collision, they would behave exactly as neutrinos do, only more so. They would feel no strong force, no electromagnetic force, and they would pass straight out through Atlas or CMS without leaving the faintest direct mark. Their entire signature would be missing transverse momentum, energy and motion gone from the ledger, carried off by something unseen. The same hole in the books that reveals a neutrino could reveal dark matter. There is, of course, the difficulty we met before. Missing momentum alone does not say what escaped. A collision that produces dark matter and one that produces neutrinos could leave the very same gap. So physicists cannot simply look for missing momentum and declare victory, because the familiar neutrino makes the same footprint. They have to look for a particular kind of event, one where the missing momentum is large and appears alongside a specific telltale visible signature, an event that ordinary neutrino production is too rare or too tame to fake. The search is for an imbalance that stands out from everything the known physics can produce. For years, this made the WIMP the great hope of the collider hunt, the particle physicists most expected to find, tied by that lovely coincidence to the weak force they already understood. Vast numbers of collisions were sifted, looking for the clean sign of something massive and invisible flying out. The strategy for finding it is elegant in its simplicity. A search for a single spray of particles or a single flash of light recoiling against pure nothingness, and it is worth seeing exactly how that search is carried out. The cleanest way to hunt for an invisible particle at a collider is to look for something visible recoiling against nothing. The idea rests once more on the balancing of momentum. Suppose a collision produces a pair of dark matter particles and nothing else. Both would escape unseen, and their momenta, being equal and opposite, might simply balance each other, leaving no gap at all. Such an event would be invisible in every way, producing no signal to trigger on. So physicists look instead for a special case, one where the invisible particles are made alongside a single visible thing that betrays their presence. Here is how that works. Occasionally, just before or during the collision that makes the invisible particles, one of the colliding quarks or gluons radiates an ordinary particle, much as a swerving car might fling off a spray of water. That radiated particle is visible. It might be a spray of particles called a jet, born from a single quark or gluon, or it might be a single photon, a particle of light. This visible thing flies out one way, and to balance it, the invisible dark matter particles must fly out the other way. Now the event is no longer perfectly balanced and hidden. It shows a visible jet or photon on one side, and a matching missing momentum on the other, pointing back at nothing. Physicists call these searches by vivid names. A single spray of particles recoiling against missing momentum is a monojet search. A single flash of light recoiling against missing momentum is a monophoton search. In both, the picture is the same and strikingly stark. One visible object flies out into the detector, energetic and alone, and directly opposite it lies a large hole in the ledger, a great deal of missing transverse momentum, with nothing visible there to account for it. The visible object appears to recoil off empty space, kicked back by something the detector cannot see. The image is almost eerie when you picture it. A single jet of particles sprays out from the collision, carrying substantial momentum, and on the far side there is simply nothing. No answering particle, no visible partner, only the measured certainty that something invisible flew off carrying the balancing momentum. It is like watching a cannon fire and recoil hard, kicked backward by a cannonball you cannot see, cannot detect, and know is there only because the cannon jumped. The visible recoil is the whole evidence for the invisible thing that caused it. The great difficulty, again, is that neutrinos do exactly the same thing. The known physics of the collider produces plenty of events where a Z-boson is made alongside a jet, and the Z-boson then decays into a neutrino and its antineutrino, both invisible. That gives a real jet recoiling against real missing momentum from ordinary well-understood physics, no dark matter involved. This is the constant background the searchers must fight. Physicists calculate very precisely how often the known neutrino processes produce such events, then look for an excess, more monojet or monophoton events than the neutrinos alone can explain, which would signal something new escaping. So far, that excess has not appeared. The counts at ATLAS and CMS match what the known neutrino processes predict, with no clear surplus pointing to dark matter. This has not produced the discovery physicists hoped for, but it has not been fruitless either. Each search that finds nothing rules out a range of possibilities, telling us that if dark matter is being made, it must be rarer or heavier or more weakly coupled than that range allowed. The collider hunt narrows the field even when it does not catch its quarry, and it does not hunt alone, for far below the surface, another kind of search waits for dark matter to come to it. While the collider tries to make dark matter, a different set of experiments waits for the dark matter already streaming through us to reveal itself. This is called direct detection, and it rests on a simple premise. If our galaxy is embedded in a vast halo of dark matter, as the spinning of galaxies demands, then the Earth is moving through that halo right now, and dark matter particles are passing through our planet and through our bodies in great numbers every moment. Most sail through untouched, exactly as neutrinos do. But if dark matter interacts even a little, then very rarely one particle should strike the nucleus of an atom and give it a tiny detectable nudge. Catching that nudge requires extraordinary conditions because the expected signal is fantastically small and rare. So these experiments are built deep underground, in mines and tunnels beneath mountains, using the rock overhead to shield them from cosmic rays and other background particles, just as Raymond Davis shielded his neutrino tank decades before. In that deep quiet, physicists place a target of very pure material, often a large tank of liquefied xenon, a heavy noble gas, kept extremely cold, and watched by sensitive detectors for the faint flash and tiny electrical signal that a single struck nucleus would produce. The scale of the effort is impressive, and it has grown over the years into some of the most sensitive instruments ever built. Experiments with names like Xenon, LX, and their successors have deployed tanks holding tons of liquid xenon, shielded and monitored with painstaking care, each generation more sensitive than the last. They are listening for a whisper, a handful of atomic recoils that would stand out from all other events as the touch of dark matter. The detectors are so sensitive that they must account for the faint natural radioactivity of their own materials and surroundings, hunting a signal quieter than almost any background. And yet, like the collider searches, the direct detection experiments have so far found no confirmed dark matter. Tank after tank, year after year, the expected signal has not clearly appeared. This steady absence has consequences. The WIMP, that favoured candidate tied so elegantly to the weak force was expected to show up by now in one of these searches, given how sensitive they have become. Its failure to appear, both underground and at the collider, has put real pressure on the simplest WIMP idea. The particle that seemed almost too neat to be wrong has not been found where it was most expected. This is a genuine turn in the story, and it deserves an honest telling. The favoured guess has not paid off. For decades, the WIMP was the front-runner, backed by that beautiful coincidence of the leftover amount matching the weak scale. But the experiments have searched much of the range where it should live and come up empty. Dark matter is still certainly there, demanded by the motion of galaxies and the bending of light, but it has declined to appear in the traps built for the WIMP. Its identity remains open, and physicists have begun to look more seriously at other possibilities. Those other possibilities are many, and some of them lead back toward the neutrino. If dark matter is not a WIMP, perhaps it is something lighter, or something that interacts even more feebly through channels we have barely begun to probe. And one candidate in particular ties this whole story together, a hypothetical particle that would be a kind of neutrino, but one even more withdrawn from the world than the three we know, a ghost to the ghost. It may not feel even the weak force, and that is exactly what makes it so hard to rule in or out. This new candidate is called a sterile neutrino, and the name captures its strangeness. The three neutrinos we know, the electron, muon and tau neutrinos, are already the most withdrawn particles of ordinary matter, feeling only the weak force and gravity. A sterile neutrino would be more withdrawn still. It would not feel the weak force at all. It would interact with ordinary matter through gravity alone, and perhaps through its subtle mixing with the ordinary neutrinos, and in no other way. Where the ordinary neutrino is a ghost, the sterile neutrino would be a ghost even to the instruments that catch ghosts. To see why physicists would invent such a thing, recall the puzzle of the neutrino's mass. Oscillation proved that neutrinos have mass, but the standard model had no natural place for it, and the mass turned out to be almost unbelievably tiny. One of the most elegant explanations for both facts at once involves adding a new, very heavy neutrino that does not feel the weak force, a sterile partner to each ordinary neutrino. Through a mechanism often called the seesaw, the great heaviness of these sterile partners could force the ordinary neutrinos to be extraordinarily light, turning the neutrino's puzzling featherweight into a natural consequence. The sterility and the tiny mass would explain each other. There is a second reason the sterile neutrino draws interest, and it links straight back to dark matter. A sterile neutrino of the right mass, not too heavy, would be a natural dark matter candidate. It would be invisible, feeling no ordinary force, exactly as dark matter appears to be. It could have been produced in the early universe in the right amount, and unlike the ordinary neutrino, which is too light and fast to serve, a heavier sterile neutrino could move slowly enough to clump into the halos that galaxies need. So the same particle invented to explain the neutrino's mass might also be the missing matter of the cosmos, uniting two of the deepest puzzles in one stroke. The recurring theme of this whole story returns here in its purest form. The sterile neutrino, if it exists, cannot be caught directly at all, because it interacts through no force we can wield. Even the trick of missing momentum barely helps, since the sterile neutrino would be produced only through its faint mixing with ordinary neutrinos, extraordinarily rarely. It is the ultimate ghost, a particle whose very definition is that it hides from every tool except gravity, and the slightest quantum leakage into the neutrinos we can see. To find it, physicists must watch for its indirect fingerprints, subtle effects on the neutrinos we already study, or a faint signal from space if sterile neutrinos slowly decay. This is honest, difficult physics, and it is right to say plainly that the sterile neutrino is not confirmed. It is a hypothesis, a well-motivated one, invented to solve real problems but not yet shown to exist. It may be the answer to the neutrino's mass, or to dark matter, or to both, or it may turn out to be nothing at all, a beautiful idea that nature did not use. physics holds it as a live possibility, neither embraced nor dismissed, exactly the honest posture an unproven idea deserves. What keeps the sterile neutrino from being quietly set aside is a scattering of experimental hints, odd results from neutrino experiments over the years that do not quite fit the tidy picture of three flavors. These anomalies are not proof, and several have faded under closer examination, but a few have stubbornly refused to go away. They hover at the edge of the known physics, suggesting there might be more to the neutrino than three flavors, and they are worth looking at directly. The hints come from experiments that seem to see neutrinos behaving in ways three flavors cannot explain. To understand them, recall that oscillation depends on the differences between the neutrino masses, and with three neutrinos there are only so many such differences, tightly constrained by all the measurements taken together. If an experiment saw neutrinos oscillating at a rate that none of the three flavor differences allow, that would hint at a fourth kind of neutrino taking part, a sterile one mixing into the pattern. Over the years, a few experiments have reported exactly such misfitting results. The first came from an experiment called LSND at the Los Alamos laboratory in the 1990s. It looked for one flavor of neutrino turning into another over a short distance, and it reported seeing more of these conversions than the three flavor picture allows. The rate suggested oscillation driven by a mass difference far larger than the three known neutrinos provide, which would require at least a fourth neutrino to explain. It was a startling result, and because it stood alone, it was not enough to overturn the settled three flavor picture. But it was a real anomaly, carefully reported, and it would not simply vanish. Later experiments tried to check it, and the situation grew more tangled rather than clearer. An experiment at Fermilab called Mini-Boon was built partly to test the LSND result. It too saw an excess of events, more neutrino appearances than three flavors predict, seeming at first to support the earlier anomaly. But the details did not line up cleanly with LSND, and questions arose about whether the excess came from neutrinos changing flavor or from some ordinary process the experiment had not fully accounted for. Instead of confirming or killing the sterile neutrino, Mini-Boon deepened the uncertainty, adding a second anomaly that neither fit the standard picture nor pointed unambiguously beyond it. There were other hints too from different directions. Some nuclear reactor experiments, counting the neutrinos coming out, seemed for a while to find slightly fewer than expected, a shortfall that a sterile neutrino soaking up some of the flux could explain. Certain experiments using intense radioactive sources reported a similar mild deficit. Each of these, on its own, was small and uncertain, sensitive to how well the expected numbers were calculated. Together they formed a loose pattern of minor discrepancies, all pointing vaguely in the same direction, toward the possibility of an extra, sterile neutrino hiding in the data. Yet the pattern has never hardened into proof, and much of it has softened under scrutiny. The reactor shortfall, for instance, came to look less convincing as physicists refined their calculations of exactly how many neutrinos a reactor should produce, and part of the apparent deficit dissolved into an error in the prediction rather than a real disappearance. Dedicated experiments built specifically to find sterile neutrinos have largely come up empty, seeing no clear sign of the fourth flavor where the anomalies suggested it should be. The hints erode, one by one, though not quite all the way to nothing. This is the unsettled, honest state of the matter, and it is worth stating without dressing it up. There is no confirmed sterile neutrino, and the mainstream evidence favours just three flavours, the count the Z boson's lifetime pointed to long ago. But a handful of anomalies persist, not yet fully explained, refusing either to strengthen into a discovery or to collapse entirely. They keep the question open. It is one of those places where physics simply does not yet know, where careful people disagree, and where the calm and correct thing to say is that we are still looking. The neutrino may yet hold a surprise, or it may not. Meanwhile, its known mass, tiny as it is, has already left a mark on the largest canvas of all. That canvas is the whole universe, and the neutrino's tiny mass helps shape how it grew. Cast your mind back to the early cosmos, a fraction of a second after the Big Bang, when everything was a hot, dense, nearly uniform soup of particles. Neutrinos were there in enormous numbers, as common as the particles of light, streaming through everything. As the universe expanded and cooled over billions of years, the slight lumps in that soup, the regions a little denser than average, pulled in more matter by gravity and grew into the galaxies and clusters we see today. The neutrinos, because of their mass, played a quiet part in how those lumps grew. Here the neutrino's nature as a fast light particle matters. Because neutrinos are so light, the ones left over from the early universe move very quickly, close to the speed of light, and they resist being gathered into clumps. Where ordinary matter and dark matter fall together into dense knots under gravity, the fast-moving neutrinos tend to stream out of the smaller lumps before those lumps can fully form, smoothing them away. A cosmos full of massive, fast neutrinos would have its finest structure gently erased, the small clumps wiped out while only the largest survive. The more the neutrinos weigh, the stronger this smoothing. This gives cosmologists a remarkable handle on the neutrino's mass. The second of the two weighing methods met earlier, and it is worth seeing how it works. The pattern of galaxies across the sky, the way they cluster on different scales, records how much smoothing took place. By mapping millions of galaxies and measuring how strongly they clump at large and small scales, and by studying the faint afterglow of the Big Bang, cosmologists can detect the gentle blurring that massive neutrinos would have caused. From the amount of that blurring, they read off the combined mass of all the neutrino types. The universe itself becomes a scale, weighing the ghost by the marks it left on cosmic structure. The number that comes out is astonishingly tight, tighter than any laboratory has managed. The cosmic measurements suggest that the three neutrino masses added together are extraordinarily small, small enough that even the whole vast population of cosmic neutrinos bend structure only slightly. This cosmic limit, drawn from the largest scales imaginable, agrees with the limit from the delicate beta decay experiments on a laboratory bench. Two utterly different approaches, one weighing a single decaying nucleus and one weighing the entire universe, converge on the same conclusion. The neutrino is real, it has mass, and that mass is tiny. There is a quiet wonder in this convergence worth pausing on. The same particle that Pauli proposed with an apology, that Cowan and Reines caught as a faint double flash that turned out to change flavour in flight, is woven into the growth of the cosmos itself. Its mass, too small to measure directly even now, is nonetheless large enough that the entire population of neutrinos left a gentle imprint on where the galaxies sit. The ghost that passes through your hand is the same ghost that helps sculpt the map of the heavens, and the neutrino's role in the universe may run deeper still, beyond shaping structure, all the way down to the most basic fact of our existence. There is a profound puzzle about why there is any matter in the universe at all, why the cosmos is made of something rather than nothing, and the neutrino may sit close to the heart of the answer. That possibility, strange and not yet settled, is the next and perhaps deepest turn in the story. The puzzle is this: when the universe began, our best understanding says that matter and antimatter should have been made in equal amounts. For every particle of matter, an antiparticle, its exact mirror twin with opposite charge. But matter and antimatter annihilate when they meet, vanishing into light. So if the early universe held equal amounts of both, they should have destroyed each other completely, leaving a cosmos of nothing but light, with no atoms, no stars, no planets, and no one to wonder about it. Yet here we are, made of matter, in a universe full of it. Somehow, matter won. The imbalance needed was slight, and stating its size makes the mystery vivid. For every billion antimatter particles in the early universe, there seemed to have been about 1,000,000,001 particles of matter. The billion pairs annihilated, flooding the cosmos with light, and that lonely extra particle in each billion survived. Everything we see, every star and galaxy, every atom in your body is built from that tiny surplus, the one part in a billion of matter that had no antimatter left to cancel it. The question is where that slight excess came from. What tilted the balance, ever so slightly, toward matter? This is one of the great unanswered questions in physics, and the neutrino offers one of the most promising paths toward an answer. The idea is called leptogenesis, and it ties the matter of the universe to the neutrino's strange nature. Recall the possibility raised earlier that the neutrino might be its own antiparticle, and that its tiny mass might come from very heavy sterile partners in the early universe. Leptogenesis builds on exactly those ideas. It proposes that these heavy neutrino relatives, present when the universe was young and hot, decayed in a way that slightly favoured matter over antimatter, producing a small excess of ordinary particles. Here is the shape of the idea, kept in plain words. Very heavy neutrinos in the early universe decay, and if their decays are even slightly lopsided, producing a touch more matter than antimatter, they would leave behind a small surplus of a class of particles that includes the electron and its kin. Through processes active in the hot early cosmos, that surplus could be converted into the excess of ordinary matter we needed, the one extra particle per billion. The imbalance that let the universe exist would then trace directly back to the neutrino, and to the same heavy partners that explain why the ordinary neutrino is so light. It is a breathtaking possibility, and honesty requires holding it lightly, because it is not proven. Leptogenesis is a hypothesis, elegant and well motivated, connecting the neutrino's mass, its possible identity as its own antiparticle, and the very existence of matter into a single story. But each link in that chain is still being tested. We do not yet know whether the neutrino is its own antiparticle. We have not found the heavy partners. The idea could be right, and it could be wrong, and physics has not yet reached the evidence that would decide. It is offered here as a live and serious possibility, not a settled fact. Still, sit for a moment with what it would mean if it were true. The faint, nearly untouchable particle that began as an accountant's fix for missing energy would turn out to be the reason anything exists at all. The ghost passing through your hand would be a distant echo of the process that let there be hands, and light, and stars, rather than a universe of emptiness. Whether or not leptogenesis proves correct, that the neutrino even could carry such weight shows how far this small particle reaches, and that reach frames the honest accounting of what, after all this hunting, we still do not know. After nearly a century of chasing the neutrino, it is worth setting down plainly what remains unknown, because the open questions are as much a part of the story as the answers. We know the neutrino exists, that it comes in 3 flavours, that it changes among them in flight, and that it therefore carries a tiny mass. That much is settled, proven by reactors and the sun and detectors deep underground. But past that solid ground, a surprising amount is still genuinely open, and a patient teacher would not pretend otherwise. We do not know how much the neutrino actually weighs. We have ceilings on its mass from beta decay, and from cosmology, tightening year by year, but no measured value, only the certainty that it is not zero and is extraordinarily small. We do not know the order of the 3 masses, which of the 3 is heaviest and which is lightest, a question physicists call the mass ordering, still not fully resolved. The very scale of the neutrino's mass, and the pattern of the 3, remain among the most sought-after numbers in physics, because they point toward whatever deeper theory lies beyond the standard model. We do not know whether the neutrino is its own antiparticle. This is perhaps the single most consequential open question about it, because the answer would reveal whether the neutrino gets its mass in a way unlike every other particle, and whether the path to explaining the universe's matter through leptogenesis is truly open. Experiments around the world are searching for an exceedingly rare nuclear process, one that can happen only if the neutrino is its own antiparticle, watching enormous quantities of material for even a single unmistakable event. So far it has not been seen. The The question stays open and the search goes on. We do not know whether sterile neutrinos exist, whether the anomalies that hint at a fourth flavour are real or will dissolve entirely under better measurements. We do not know the full story of why neutrinos oscillate the way they do, whether their flavour changing hides a subtle difference between matter and antimatter that could help explain the cosmic imbalance. Dedicated experiments now running and being built are aimed squarely at these questions, sending neutrino beams across countries and watching for the faintest symmetries that would carry the answer. And of course we do not know what dark matter is. The Clyde hunt and the deep detectors have not caught it, the favoured WIMP has not appeared where it was expected, and the field has widened its search to lighter and stranger candidates, sterile neutrinos among them. The most abundant matter in the universe remains unidentified, mapped by its gravity, hunted by absence and still unclaimed. This is not a failure so much as an honest frontier, one of the clearest signs of how much physics is left to learn. It would be easy to present all this searching as a story of triumph marching toward completion, but the truer picture is calmer and more interesting than that. The neutrino has been studied for almost 100 years by some of the finest minds in science, with instruments of staggering ingenuity, and it still holds secrets. Each answer has opened new questions, and the deepest ones, about its mass, its nature, and its role in why the universe holds any matter at all, are still being worked out right now, in laboratories buried under mountains and in tunnels beneath the countryside. That is the real state of the hunt, patient and unfinished. The ghost has been caught again and again in reactors and mines and now in a tunnel at CERN, and yet it keeps a little of its mystery each time. Which brings us back after this long journey to the simplest question, the one asked at the very beginning, and to what all this means for you. At the start, a simple puzzle was set. How do you catch something that goes through everything? Now the answer can be given plainly, because the whole story has been the answer. You catch it by patience and by cleverness. You cannot catch a neutrino the way you catch a ball, because it almost never touches anything. So instead you gather an enormous number of them, or an enormous amount of matter for them to pass through, and you wait for the vanishingly rare moment when one of them snags on a single atom. Or, when it is made inside a collision, you catch it by its absence, by the exact hole it leaves in the ledger of momentum. You catch the untouchable by being more patient than it is elusive. That is how something we cannot feel was found, and found again and again. Wolfgang Pauli proposed it in a letter, half apologising, to save the conservation of energy. Enrico Fermi built it into a theory and gave it its name, the small neutral one. Clyde Cowan and Frederick Reines caught it at a reactor as a faint double flash. Raymond Davis counted too few of them from the sun, and that shortfall led, through decades of careful work, to the discovery that neutrinos change flavour and therefore carry mass. And at CERN the same particle is inferred from missing momentum and, in a tunnel down the beamline, has at last been caught in the act. Return now to your own hand, held up to the light where this began. It still feels solid, warm, entirely your own, and the 100 trillion neutrinos still stream through it every second, from the sun overhead by day and up through the whole Earth by night, touching almost nothing, leaving almost no trace. Nothing about that has changed. What has changed, perhaps, is that you now know they are there, and you know a little of what it took to find them, and to prove that the emptiest seeming thing in nature is real. Widen out then to what this means. The neutrino is a reminder that the world is full of things we cannot see, and yet can come to know. Most of the matter in the universe is invisible, and most of the neutrinos passing through you right now began in the heart of the sun 8 minutes ago, or in the first seconds of the universe billions of years ago. You're not separate from all of that. You're made of the matter that survived the Great Annihilation, perhaps because of the neutrino, and you are being passed through, constantly and harmlessly, by particles that carry news from the centre of the nearest star. There is a particular kind of calm in that. The universe is not only the solid things we can touch, it is also this quiet, ceaseless traffic of ghosts, mostly ignoring us, occasionally caught, slowly revealing themselves to anyone patient enough to build the right trap and wait. The neutrino asks nothing of us and touches us almost not at all, and yet by studying it we have learned how the sun burns, why the standard model is incomplete, how galaxies took shape, and maybe, someday, why there is anything here to ask the question. So the next time you hold your hand up to the light, remember what is pouring through it, unfelt and unseen. The ghost is real. We found it. And in learning how something can go through everything and still be known, we learned a little more about the strange, mostly invisible universe we're quietly part of.